Hi, my name is Tonatiuh Matos, and the name of my talk is Physics and Cosmology on a Gravitational Wave Background.
There is a strong belief that we live in a gravitational wave background. This is because during the Big Bang, the production of gravitational waves was very, very strong. After that, for example, inflation produces also a lot of gravitational waves. And after that, maybe phase transitions and production of primordial black holes produce also a very, very strong amount of gravitational waves. And today, collisions between black holes and even the movement of these planets around these stars, stars around the galaxies, galaxies expanding in the universe, all of them are producing gravitational waves in a lot of them.
Therefore, I will start with the hypothesis that space-time is stochastic, it oscillates, and we live in a gravitational wave background. In order to show that, I will give a very short mathematical introduction. Then I will speak about geodesics, the Einstein field equation, and cosmology. As you know, the Einstein equations are formulated in a smooth manifold. That means this is a topological space which open sets are isomorphic or homeomorphic to the Rn, in this case to R4. That means that each open set is like this piece of paper, very, very flat. Nevertheless, if we live in a gravitational wave background, that is no longer true. These open sets should be something like this lake, more than this piece of paper. In other words, these waves or these waves in the water are very similar to the waves in the gravitational wave background. I will start with the formulation of the Klein-Gordon equation in a U1 invariant field. That means this is a Klein-Gordon equation together with an electromagnetic field. In that case, what we have is the formulation of the Klein-Gordon equations and the Maxwell equations. And the source of Maxwell equations of the electromagnetic field is this current, where this current is provoked by the scalar field and the electromagnetic field. Here, it's important to say that we can write the scalar field potential in this way in order to get something easier. Well, then we start with the foliation of the spacetime. This is a standard formulation in 3+1 metric, where this t is not the time, but is the evolution's parameter.
In other words, we perform a foliation of the space-time where t is the evolution's parameter of the space.
Now we perform a transformation. This is called the Madelung transformation here. And it consists in to write the scalar field or this function in terms of the norm, and its phase. And in that case, we can separate the Klein-Gordon equations into its real part and its imaginary part. The important thing here is that the current collapses in a very, very small and very, very simple expression where we can define this pi as a velocity. And we will define this pi mu as a velocity of the particles in this formulation. Well, now we rewrite again the Klein-Gordon equations, the real part and the imaginary part here, but now in terms of pi and n, the number density. And you know, these are the Klein-Gordon equations, but now written in terms of the velocity and the number density. And this is very important because I will use this formulation in the next slices. Well, now we come to the physics. Well, if you have 2 points and you want to go from one point to another point in this flat space-time, in this local flat space-time, you go from one point to other point in through the straight line. But if we live in a gravitational wave background, this is no longer true because you have to take into account the waves. And for a small particle, this motion will be a stochastic motion through the waves, through the gravitational waves. Well, in order to introduce the stochastic motion into the Einstein equations, into this formulation, we define two derivatives. The first derivative is the normal derivative, and we take the difference between 2 points here, and this is the normal derivative, as you know. But now I can define a second derivative, and this is the derivative which takes into account this displacement and this displacement here. And you see this derivative is given here, the stochastic derivative, and take into account these two displacements. Well, in this can be defined, or we can be expand in series, and you find this one and this one as the normal operator, derivative operator, and the stochastic operator. Well, we can define with these operators, of course, the normal derivative, the normal velocity, and the stochastic velocity given by u, v and u. This is the stochastic velocity, and this is the other one is the normal velocity. Well, the next step is we make these definitions, but in terms of covariant form. Well, the covariant way, this is the normal derivative is given by this expression. This is the normal derivative. But for the stochastic derivative, this is the expression. But this is the covariant way to the covariant form of this stochastic derivative. And with this stochastic derivative, of course, we can define the new velocity, the normal velocity, and the stochastic velocity. This is very important. Well, then with these velocities, we can define now the displacements. Well, the forward displacement here is given by this dx file, and is defined in the way that we can go forward with these particles in what we have to take the velocity and the stochastic velocity together. And the backward velocity is only to take of course, the velocity and the backward velocity in the way of the stochastic velocity. Well, with these displacements, we can define the Fokker-Planck equation. And the Fokker-Planck equation is not other thing that the sum of this one will give us these equations that we know that is equal to 0. This is the continuity equation, but the difference between these two equations give us this definition, and this is the stochastic velocity in terms of the normal number density. This is a very interesting definition. Well, then we can to find the accelerations. The accelerations, of course, is to take the derivative of the velocities. Then this is the normal velocity to the normal operator to the normal velocity. This is the stochastic the derivative to the normal velocity. And this is the stochastic operator, the stochastic velocity to the normal velocity and to the normal and the stochastic velocity to the stochastic operator. This one is defined as the quantum force. And this is very important because this quantum force was defined by Madelung many years ago. Well, observe that if we take the normal operator, the normal derivative to the normal velocity, this is the direct definition, yes, here. And this can be rewritten in this way. And this is exactly the definition of a vector with integral curves are exactly the geodesics. Then, in other words, this pi mu defines the geodesics in this space-time. Then they are really, in reality, the velocity. Well, then we taken out all the accelerations, all the accelerations we calculated. And we know that the mass times acceleration is equal to the force. But now it's equal to the forward force and to the backward force. And we know that the forward force is the electromagnetic force and the external force given here. And the forward force remains as same, so as it is. Well, we make all the sums of all of them, and the first way we find is that this term here is the continuity equation. The continuity equation is equal to 0, therefore this term is equal to 0. Well, then we see that the external force here, defined here, yeah, is here. Then this is the external force, and we remain with that. Then the electromagnetic force is defined here. This is the Lorentz force, and you see this is here, and this other side of the equality. Then these two terms they cancel. Well, and the forward force is given by this expression here, and therefore what we have to the end of the day is that equation here in terms of the velocity. This is this term here together with the integration constant and the acceleration here. Well, in other words, this is not other thing that the Klein-Gordon equation, again, written in terms of the velocity and the number density.
In other words, in a gravitational wave background, the space-time is stochastic, and particles in a stochastic field follow the Klein-Gordon equation, where the phi function can be separated into its norm and the phase. The norm determines the stochastic velocity, and the phase determines the geodesical velocity. And the important thing here is that the Klein-Gordon equations in the Newtonian limit is the Schrödinger equation. In other words, the Schrödinger equation is a consequence of the gravitational wave background of the space-time, of the stochasticity of the space-time. That means that we don't need the uncertainty principle to determine the Schrödinger equation.
So we arrive to the first conclusion. Gravitational wave background or fluctuation in space-time can explain the quantum behavior of quantum particles. This implies a completely new interpretation of quantum mechanics.
On the other side, these gravitational waves have energy, but this energy is not contained in the Einstein equations, because this energy is not a source, it's a property of the space-time, it's a fluctuations of the space-time. Therefore, it should be contained in the Einstein equations, and it is not.
The next step is to introduce the energy of the gravitational wave background into the Einstein equations. In this publication here, we were able to show that this energy can be added into the Einstein equations if we add this term, 2 pi squared of lambda squared, where lambda is the wavelength of the graviton we are taking into account. Well, but remember, this wavelength is going up because the universe is expanding. Then, after a while, you have the wavelength is bigger, and it grows up at the light velocity. Well, in that case, we know that everything that goes at the light velocity, then it should perform this equation here, and this is the equation for something that is going to the light velocity. From here, we can obtain the length of the wavelength, and this is given by this one. Well, then I will call the Compton mass dark energy model this one. If the Einstein equation are written in this way with this extra term is 2 pi squared of lambda squared, and lambda is growing up with this integral. And then I will call it the C-made model. Well, then the next step, of course, is to write the Friedman equations. The Friedman equations are given here, but because we have this new term, we have to add this term here in this part. Okay, we can make some mathematics and obtain the corresponding density, rate density, and with them we can obtain the Friedman equations. And the corresponding Friedman equations are given here. But there is a problem, because if you remember, these waves, these gravitational waves are energy, but some part of this energy is contributing to the expansion of the universe. But some part of them are contributing, for example, for the large-scale structure formation. Well, then we have to add some bias parameters. For example, here's an interchange between the dark matter that we don't know and the gravitational wave energy. Well, but how much of them are interchanging between them? Well, we introduce this bias parameter in order to valorate this amount. And how much of this is expanding the universe? Therefore, we introduce this bias parameter in order to know how much of them is expanding the universe and how much is, for example, producing a gravitational large-scale structure of the universe. Well, the first what we find is that they both are very, very similar. You see, here is the growth of the Hubble parameter. They are really very similar, and the difference is given here, and it's less than 7%. Here, they are really very similar. That is fine, because we can then compare that with the observations. And the first comparison with observations tell us the following. We compare that with cosmic sensors, baryon acoustic oscillations, supernovae, and the Planck observations. And then we obtain the chi-square from all of them. And what we obtain is something surprising. The difference between the chi-squares between the lambda cold dark matter and the CMATE model is 3.65 in the favor of the CMATE model against the lambda CDM. And the values of the Hubble parameter today is 69.9 kilometers over second over megaparsec, and the other values are given here. And now I am going to remove the Planck observations in order to compare the far away and the close by observations of the universe. Well, in that case, we remain with the CC and BAO and phantom observations and compare that with the lambda CDM model. And again, we obtain the chi-square data, and we obtained 3.25 in favor of the CMATE model against the lambda CDMA model. And now the Hubble parameter today is 68.3 kilometers over second over megaparsec. Here we have the confidence level of all of these observations. But now I will take only the Planck observations, only the Planck observations, only the Planck data, and now the fit is again very, very well. And you see now the H0, the Hubble parameter today is 68 kilometers over second over megaparsec. That means that the H0 tension reduces very, very nice. In that case, we can come to the conclusions. First, if we take into account the gravitational wave background, the Einstein equations can be transformed in this one, with this extra term, where the extra term is 2 pi square over lambda square, where lambda is the wavelength of the gravitons. Then the geodesics can be performed, can be obtained, solving the Klein-Gordon equation, where from the phi function we can obtain the geodesic velocity and the stochastic velocity. And the last conclusion is that the energy of the gravitational wave background or fluctuation in space-time seems to be able to explain the accelerating expansion of the universe very well without the need of cosmological constant, exotic extra matter, or modifications of the Einstein equations. Thank you very much.